Hello, this is a video on my third attempt to prove P equals NP. So my third attempt was by far the largest. Hopefully I will be able to explain it sufficiently. So let's get started. To start with, you can think of a CNF equation as a series of triple literals. So you can think of this as a clause, this is another clause, this is another clause, where each of these dots is a literal inside of the clause. And so it's aliteral, it's either true or false. And the goal is to find a solution, and a solution is a path such that it touches one literal in each clause. So that's a path, that's a path, that's a path. And the only rule is that if a path touches a literal, it cannot also touch the negation of that literal, because the path is essentially a permutation of the solution. Your solution cannot contain A and not A. So if you go here, then you're saying that A must be true in your solution, and that holds for everything else. Obviously, this is exponential. There's an exponential number of paths you need to check. In fact, it's a bad exponential. It's 3 to the power of c total possible paths, which is not good. C is the number of clauses is greater than the number of literals, so you're better off just doing 2 to the power of the number of literals, and that's just trying every possible solution. So the question was, could I do this in polynomial time? The first thing to note is that there's a trick that each path at position, let's say B is position 2, at position 2, each path will have one of these three values. At position 3, we'll have one of these three values. So knowing that, you can simplify the values inside of the path. My idea was essentially to store pointers. So the notation will be a bit weird. These are literals, but I might call them nodes or vertices. And these could be edges or pointers. So it all means the same thing. Essentially, I would store the number of paths that pass through a certain point. So if you have a path like this and a path like this, then you have two paths passing through this point, one path at this point, one path at this point, so on and so forth. Alternatively, you can even go bigger and instead of storing just the number of paths that go through a point, you can store the number of paths that go through an edge. So like take this, how many paths go from here to here? So let's say we have 3 paths. We have this path, and we have that path, and we have this path. Well, the value here will be 2, because 2 paths go from here to here. The third path, of course, goes from here to here, so it doesn't count. So I will use a value known as I, and I is the length. So if I is 1, then we're storing the number of paths that pass through a point. If I is 2, we're storing the number of paths that go from a point to another point. If I is 3, we're storing the number of paths that go from a point to a third point. So they must travel this entire distance. So that's just I. Just remember that. So generally speaking, the difficulty, first I should note that for a value of I, the amount of storage space would be c to the power of I. So if I is 1, then we just store one value, well, 3 values for each clause. If I is 2, we store every path. And so it's I squared. Oh yeah, I should note, the reason why it's I squared is because we don't just store the path from A to B, we also store the path from A to C. So for any clause and any clause after it, we store the path. Or if I is 3, then for any clause with a clause that comes any point after it, with a clause at any point comes at any point after that, we store the arrow from that to that to that. So that's just so we can have it be arbitrary. So that's the space. As you can see, I is a constant, therefore it is still polynomial. Like it's c squared, c cubed. So it's bad, but it's not terrible. So now let's get into how we would actually update the values, because that's the most critical part. Essentially, you have the values, you assume they're correct, and then you add in a new clause. Let's call it a prime. So a new clause. And it has 3 values. And keep in mind, it has 3 literals. Keep in mind that all the values we're storing are just the number of paths that pass through a point, or pass through 2 points. So essentially, what we can do is we can just add in one new literal that all the paths must pass through, figure out how many paths actually can pass through it, and then do that for all three of them, and then just add up all the paths. So if you have a path that goes through here, and a path that goes through here, but doesn't go through here, well then basically you just have this path and this path. It's the same path. Well, not the same path, but you can just add them up. It's trivial. So really, adding a new clause means just adding in a new literal. Now let's look at how do you add in a new literal. Well, let's say we just added in clause A, right? We had B and C, and now we just added in A. And so we're just looking at one new literal in A. Seems pretty simple. How do we handle that? Well, it's pretty simple. We know the exact rule we have to follow. If we have A, it cannot go to not A, because they're mutually exclusive. So basically what that means is all the paths that go through A are now 0. All the paths that go from A to anything else are now 0. All the paths that go from anything else to A are now 0, or to not A in this case. They all get zeroed. And then we just propagate that out. Which means that in reality, when we do this, all we have to do is update one of these at a time. So if we add in the literal A, we just go to each not A one at a time and zero all of them. And to zero that, one last simplification is we can think of it as the ghost clause, is what I call it. So let's say we have not A, node, and then we have some other clause B, which has 3 nodes, and some other clause C, which has 3 nodes. And keep in mind we have, let's say I is 2, so we have basically the number of paths going from here to here, from here to here, all the one long vectors, basically. So essentially, we can use the fact that not A is now 0, and all these are not 0. So we know what this is, which means we can actually figure out if I is 2. Actually, let's set I to 3. So we have a third clause here. So we have this guy, it's all zeroed. So what we're trying to solve for is this path, and this path, and this path, all these paths that go through 3 vertices. But since we know this guy, we know this path, and we know this path, right? We know all the 2 long paths. We know this path. So number of paths that go from here to here to here, which means that if I is 3, we know all the values for I equals 2. So the question is, knowing the I equals 2, can we solve the I equals 3? So keep in mind all these simplifications took about 2 months to figure out. So yeah, this was not trivial. But basically now we've reduced it to just, if you have a series of values here, and you know this value and you know this value, can you solve for all the 3 long values, knowing only the 2 longs? Or knowing I minus 1 longs, can you solve for I longs? So how do we actually do that? Well, you can write it out as a linear equation, because essentially the number of paths going from here to here is equal to the number of paths going from here to here, here to here, and here to here. So essentially, you have a series of variables, in this case 27, because there's 27 possible paths going through here. 3 times 3 times 3. So you have 27 unknowns, and you have a series of equations where you have unknown 1 plus unknown 2 plus unknown 3 equals known value. And this is essentially a linear programming problem, specifically an integer programming problem, so it's non-polynomial, but we'll ignore that for now because it doesn't matter. Even if it was polynomial, it would still fail. So now I will go over to some code I wrote to actually generate that series of chunks, or that it generates the matrix of equations that you would solve. So first off, we can see that when I equals 1, essentially we have 3 nodes, and we know the total number of paths that go through all of them. Like, we know the sum. So essentially it says that vertex 1 plus vertex 2 plus vertex 3 equals the unknown. Now we can look at I equals 2, where we have these guys. Basically we have 2 clauses, and we know all the paths between them. So we know 1, 2, 3, 1, 2, 3, 1, 2, 3. And so we know that path 1 plus path 2 plus path 3 is equal to this value right here. And we can see in the thing, path 1 plus path 2 plus path 3 is equal to a value. And these three are also equal to values, so that gets all the ones leaving here and all the ones leaving here. Then the lower values, you can see we have 1 in each, and that's because these are the values coming to here. These are the values coming to here and coming to here. So you can see that it generates them properly. So now I will alter the code slightly by getting rid of the thing that shows the matrices and put in the thing which shows the rank. Because the thing about linear programming is that whether or not we can solve it is based on the rank. If the rank is equal to the size, then we can solve it. And so now I will run it one last time, and this is the part that wasn't so fun to see. I will now change this to 10 because I forgot to do that. I'll now run this one last time, and we can see that as I increases, so this value is I. This value is the actual number of things we have to solve for. So the first thing we were solving for 3 values, as we can see. Second thing, we were solving for 9 values because there's 3 starting and 3 ending, so it's 3 squared. Next thing, we're solving for 27, obviously. Here we can see the rank of the matrix. So here the rank is 1 because we know the sum is 1. We know the sum, that's one known value, but we need 3 values. For the next one, the rank is 5. That is because, because it just is. There's six equations, as we can see, but it's linearly dependent because any one equation can be made with the other 5. So essentially, we can see that as I increases, you can actually see the difference between the rank and the number of things we actually need to solve for increases by an exponential, 2 to the power of I, essentially. We can see that the difference between how much we need and how much we get goes down. So the number we're solving for goes up by a factor of 3 to the power of I. Meanwhile, the unknowns go up by a factor of 2 to the power of I. But the fact remains that even though we get closer, it's still, it never converges. It only gets further apart in terms of the actual number of unknowns, which means that increasing the value of I will not make it solvable, which is sort of the nail in the bucket, or the nail in the coffin for this proposed solution. Basically what it shows is that if you have all the vectors of length I minus 1, you cannot solve for all the vectors of length I, at least not deterministically. So that's why this doesn't work. In theory, there are some inequalities you could use to narrow the search space, but the fact remains that when adding in a single clause, you need to solve this many times. You need to solve it like 3 to the power of c times, or even more, because there's all these different updates. For each not a, you have to update 3 to the power of c. So there's a lot of updates. And if you can't solve a single one, you would need to branch into every possible solution. And so even if you only branch once for each new clause, that's still 3 to the power of c branches, or 2 to the power of c branches. So it's still not good, which is why this failed. I know I didn't do much drawing. It might not have been super understandable, but it does work out, and it's impossible. And this was about 2 months of me thinking about it. At this point, I'm pretty sure P is not equal to NP, and I'm actually working on proof that it's not equal. So if that doesn't work out, I'll post a video, and if it does, I'll post a video after I win $1 million. Until then, I hope it was at least interesting. Thank you.